set-value dynamical systems. So you're describing the aggregate behavior of random dynamical systems with bounded noise. So we have already seen some examples where I used this. Maybe the first example was in the first lecture, where I very quickly observed that every point converges to some set E, which is a Cantor set. And basically there was some kind of like set-value approach. It's not true that every orbit converges to this set. In the orbit it's just a randomly jumping point. The trajectory is not E, but it actually condenses into the set E, and the set E was important because it was the support of the stationary measure. Yeah. So when I talk about accurate behavior, it's somehow like markov process for the one point. So and we also saw that in the circle map example, I indicated very quickly some regions where now the orbit would converge to. Of course, the orbit then erratically behaves within this region, but again, it's support of the stationary measure sits in there. So, important aspect here, maybe is the first slide, is to say something about noise. So, what kind of noise do we have? So there's basically some kind of dichotomy. There's a kind of unbounded noise, which is very popular, and happens, I think, in most studies of random dynamical systems, or one way or another. But there's also an option for bounded noise, and I think they're concepts which are different, and sometimes it doesn't maybe matter, and sometimes it matters what you do. So it depends what you're interested in. So one of the main reasons is that I think to use bounded noise is that from a modeling point of view, this is often really what people would like to see. So if we have some physical system where we say we have an input with some variation, usually don't mean that the variation is basically unbounded. We usually mean that the variation sits within a certain region. Now when we model that, of course we have a certain habit of thinking, well, maybe it's a normal distribution with a certain variance, and then somehow these events that are very far are very unlikely. So we can actually work with a theory where we have these taking events into account, but they have such a low importance that it doesn't matter. And so why do we do that? Because of course we can then use the tools from mathematics, the use of distributions. And so we know how to do with normal distributions, maybe some finite distribution could be a little bit more complicated. So there's a mathematical technology designed to work well with this unbounded noise. But it has bad consequences, especially when you do dynamics and you take limits of time go to infinity, that all those things that are very unlikely suddenly become kind of very possible. Because if you have something which is very unlikely and you wait very long, then somehow this might well happen. So it doesn't really. So these limits don't really work. So this is a problem. So we get some kind of counterintuitive issues popping up if we have unbounded noise and we have time to infinity. For instance, simple type of conclusion is if we have a system with unbounded noise, then and I have a system on a dynamical system, the basically there's only one attractor. Why is that? Because I can go from any attracting set to any other attracting set through the noise, so there's only one attractor. Now, that's conceptually maybe not so nice. We want to think about bifurcation theory, for instance. You want to think that maybe you could go in the basin of one attractor, but you can sometimes be in the basin of another attractor, and maybe that's important to emphasize that. And if you have unbounded noise, then the theory becomes very vague in this sense. It says like, well, we have actually one attractor, and maybe you're a little bit more in one region of this attractor than in some other region, or you have some region of density. Of course, in some sense, these things are equivalent, but maybe it's very difficult mathematically to make a statement that would say something interesting about where you are. So I think, as an aspect of the modeling, we have to take models that enable us to make statements that are in the direction of what we are to answer questions that we're interested in. So there are consequences to take a certain type of model, because sometimes because of the model, we cannot answer a certain question elegantly. We can give some number somehow, we can compute a number, but we can maybe not formulate a theorem that says that something is true. And so I think that there's a general problem in modeling. Is the type of model you choose a PDE or a lattice equation, or a stochastic differential equation, or a random dynamical system with bounded noise, or whatever you do, there's a consequence for the kind of model you take, of what kind of answer you can obtain. So, nature is not the model, nature is doing its own thing. But we take a model and we try to understand reality through such a model. So there are consequences for that. So I would say there's a strong case to work with bounded noise in dynamical systems, because it enables us to see much more topological features of the dynamics than when we have unbounded noise. If we have unbounded noise, we blur everything into one thing. If you look at stationary measures, they have full support, all these things, and it's kind of not very useful. So one of the problems with the, I think it's what I want to pop up here. Yeah, one of the problems here, for instance, with this pitchfork that we saw with an unbounded noise, we always have a stationary measure with unbounded support, full support. And then what we get is, if you look at distributions, you get this behavior where you see some features of the distribution changing, but it's difficult mathematically to kind of make sense of it. And so maybe if we have a situation, where I have this, this situation with this double well, where we have a high barrier and relatively low noise, we really would like to think that we have some distribution that sits here, which actually has zero probability in the middle. Right? So we sit either here, or we sit here, but we don't sit really in the middle. We can't jump. But with unbounded noise, we can always jump. So with unbounded noise, there's always a very low probability here. Of course, we can try to compute this probability, it will be very small. But for topological theory, this is not very nice. So that becomes something where we have to describe numbers, where actually we'd like to say, well, we'll always stay here, we'll always stay here. And so with the unbounded noise, we don't have the choice. Now, if I do bounded noise, then of course I can easily have this. I can easily make the noise in such a way that I just never can jump this barrier at all. And that means instead of having one attracting set, I have two attracting sets, which is much more like the deterministic case. So in the deterministic case, we have lots of topological tools to use. If you have unbounded noise, we lose a little bit our topological setting, and bounded noise has the advantage that we can actually see some topological features. Okay, so why I'm interested now in this bounded noise? Because with the bounded noise, I can have different stationary measures at the same time being present, and I can ask myself how, say, suppose that the stationary measures represent, say, attractors or something like that. I can kind of ask, like, can we have new attractors appearing? Can we have attractors disappear? We can have interaction between such objects. And this is very similar to what we do in deterministic dynamics when we talk about bifurcation theory. So, in some sense, in the unbounded case, there is not so much to do. So first, I wanted to make the case that I think bounded noise is interesting. I think it's interesting for applications. As a caricature, I always say, like, if someone comes from, say, life sciences with a model with probability or noisy model, and it goes to math department, then the math department, they send them to a stochastic analysis person who writes down a beautiful stochastic differential equation and says, this is what you need to do. And then somehow this is what taken. But there is, of course, consequences to that approach. I think if you ask the same person to draw up a model by themselves of something what they think is going on, it probably much more looks like something with a bounded noise. They probably write down something, and there's some variation of something somewhere. And the mathematician would translate that into, well, maybe this is not really workable mathematically, we don't know how to prove anything about this, and we change it. So I don't say that all problems should be bounded noise, but it was a fantastically sensible problems in stochastic differential equations, but I think there's a lot of practical problems that lend themselves for it. But we don't have the technology to say much about it. We don't have ways of solving such equations analytically. So there's a lot of kind of barriers there. If you say simple model, but then I don't know what to do. And of course, then we can say, let's simulate We can of course simulate bounded noise very easily. You put on the computer and you just. But then the question is, what should one compute? And simulation is very expensive in some sense. That's a very brute force thing. So you could ask, like, can I do something else than simulation, which tells me something about such a system which is more efficient to compute? And I think we need some mathematical theory for that. So if I have a model with bounded noise, can I find something out? Computation. Okay, so one of the ideas then is to look at sort of set value dynamics. But let me first look at this example of a system with bounded noise. I'm basically looking at the pitchfork example, but not at the stochastic differential equation, but at the mapping. And here's a mapping, and this precisely gives you a pitchfork behavior if the noise is absent. So this is a mapping, x plus 1 gives you some function, and I will see a graph of it soon. And here is a noisy term, just additive noise, but now I assume that this psi is just inside a bounded interval. It's a bit like we did with the circle map already, right? And the circle map also with the bounded noise. And then here we have a classification diagram in alpha x space for the case that sigma equals 0, and this is exactly the picture also in the pitchfork. That's exactly the same. This is a discrete analog of this. And if you now look at the numerics, you see something like this, and we saw it also in the circle map before, that we have a bifurcation diagram where we have some kind of like, range is just a sketch, it's not numerics, where we have some point, and here's the bifurcation point of the deterministic system. I don't really see so much, but at some point we see that the support of the set breaks up abruptly into two pieces. So we saw it actually from the other side. We had this thing with the period 2 point, which is similar. We had two regions, and at some point these regions just collapse into one region. That was on the circle, but now here it's on the. And so if you look at such orbits, they go run around in such a region, so the stationary measure will sit on it. And so the idea is now to try to understand such changes for the random dynamical systems in a derived set value dynamical system that ignores all the details of the noise and just looks at basically the kind of topological bifurcation, but it removes the details of the noise, but basically look at the set value analogous analogy of the Markov operator. And so of the Markov process. So instead of actually pushing measures forward, I just put space forward. So I'm just looking like what are all the positions where I can end up with in one time zone. And that's a set value. Okay, so the idea is that I don't really want to know what the distributions are in here. I'm not going to be interested in that. I know there's some distribution, but I want to extract only the topological information, and hopefully this gives me a reduced model. This is maybe more easy to deal with than with the whole thing. And so in general, I'm interested in this random number system bounded noise, and maybe of a very specific type. Initially, I think that intuitively this is a very nice set of models where I just look at the deterministic model, and at each iteration I just add a random point in a small ball. So I just look at a small ball, and sigma is the radius of this ball. And that's precisely what also is in the so the collective behavior now is a mapping, which is a set value mapping, and is generated basically by associating a point with a point, a map F, which gives you an image which is a set. So what's the set is the point f of x, and then taking the sigma ball around it. And so the set, and of course now I can extend it to sets by just taking the image of a set is just a union of the image of individual points in this set. So pictorially speaking, it's following. So I take a mapping and then I assume some slight noise around it. So then in the end, this point is mapped to this set. And so in a one-dimensional case, I have one point mapped to an interval. This is a very naive model of noise. So what I'm not saying here is actually what the distribution here is. I just say that the support of the distribution, if there was a random system in the background, was precisely on this ball. But I'm not. So of course there will be some details that I'm now ignoring. But of course I want to reduce description, so I will not gain information about probabilities, but I will only get information about the set-wide behavior. And so similar strategies are developed naturally in control theory. In control theory, one would be interested, for instance, in some behavior plus something where I can steer the system in a certain direction. And then you want to know kind of what can happen in, is the system controllable or not, or so on. There's also set value methods for that. So there's a very close relationship between set value dynamics for random systems and for control systems. Good. So what is the context that we work with? Well, we work with Hausdorff metric, and we have introduced it before. So I work with sets, and I want to compare sets. And so it's natural to put the Hausdorff metric on the base space of compact sets. So we have done it before, so maybe I don't have to go over this again. And so this is kind of a well-behaved metric, because in the end, now my objects are dynamics is with sets, and I want to know whether sets converge to something. So I want to have a metric to see what the distance is between sets and so on. And another thing which is important, you have to have some reasonable sense of lim sub and lim in, and these are in these settings. I will not deal with it in detail, but it's important to understand that we have to make such a concept that doesn't follow ab initio what the definition should be. But these are standard definitions in such a context. You must make sense what it means to have a lim sub limit of a number of sets. The lim. Good. So, what are we interested in? We're interested in the so-called invariant sets. So, an invariant set is a set that's just invariant of the map F. It's just a set-valued map. So, it's invariant if you have F M plus M. And we call it the invariant set minimal if it doesn't contain any proper F invariant subset. Okay. So, why are these minimal invariant sets important? They're important because stationary measures of underlying system are precisely having their support on such minimal invariant sets. So the minimal invariant sets of the associated set value systems are precisely the supports of stationary measures, and vice versa. So there's this correspondence, which is very important. So not just an invariant set, it has to be minimal invariant set. Stationary measure sits on minimal invariant set, not on invariant set. Okay, so this is important. So when we want to know something of these things, then we can work with the set value context. And so maybe the strategy for the random dynamical systems in this context is that I've argued in previous lectures maybe against the stationary measure as the solution to all problems, but maybe a part of the solution. And so if we want to know what happens to our dynamics, maybe we first want the first picture we want to get is like, where are our stationary measures? And when we have our stationary measure, then I can find which dynamics is taking place under the hood of the stationary measures. So it is quite reasonable to first understand this topological setup and see which stationary measures we have, and then we can always ask what dynamics is underneath it. Of course, this set-value approach doesn't give any information about the underlying dynamics. It just gives information about stationary measures. So if I find a minimal invariant set, I know there will be a stationary measure on it. And if invariant sets disappear, then stationary measures disappear. And then the associated dynamical features with it will also change. Okay, so simple example, quite elementary, but quite important. So let's assume that our mapping F, that is underneath this system, is a contraction. So that means that we have a Lipschitz constant to this property, and the statement is that for all sigma positive, the mapping capital F, which is basically this sigma expansion of the map little f, is also a contraction on K of x with the Hausdorff metric. And the unique fixed point is of f is unique minimal invariance. And so minimal attractors of this type persist minimal invariance sets of small perturbation if there's a contraction. So we have that's kind of obvious. Okay, so how do you prove such a thing? So we have so we start with a map which is a contraction, and now I expand it. And the question is like, why does it now also give me a unique invariant set? Basically, you have to. You can see this dynamical system as the composition of two mappings. It's first a mapping by the map F, and then by the expansion. And the map F has a Lipschitz constant smaller than 1, so the only thing that I have to show is that this expansion by sigma doesn't really kind of also have Lipschitz constant which is not more than 1. Because then the Lipschitz constant of the composition is just a product of Lipschitz constants. So we just have to kind of check these things, and you can do this by just checking basically what the so H is here the Hausdorff metric. So I want to kind of basically measure what the distance is for these things, and this is basically writing out the definitions. And if you definition, you see that if you look at the difference between these two sets where x is an A and B, so these are basically two sets that are sigma inflated, then the Hausdorff distance is larger or equal to this object. But we can also get this kind of bound. We also see that this thing can be written now. These are kind of like tedious things. This is typical of this analysis. But we have to analyze these things. There's not much to be said about it. It's just like messing around. Then we can see that this inequality exists. Also, we have one here, which is a then we have say that this distance here. This is a upper. This distance here, and then we see precisely this. We see that the distance between these two inflated sets is bounded by Hausdorff distance. And because it's symmetric, now we can take the Hausdorff distance, but the symmetric is both of them are smaller, and if we get the maximum of both, we'll see the Hausdorff distance of these two sets is smaller equal than the Hausdorff distance between A and B. And so it means that I do this inflation by sigma, and I don't really create any kind of more distance between two sets in Hausdorff distance. And if my other map is just a contraction, then I see that I don't really do any harm. So of course, if we have an inflation mechanism that actually does have some expansion features, then there's a balancing between the two things. So it could be that I just take now uniform balls. I could also take something else. If I take something else, it's possible that this actually has a positive Lipschitz constant, and then I have to make sure that my contraction is strong enough to overcome the positive Lipschitz constant of the inflation procedure. as I say, my inflation procedure here of the epsilon ball is just a simple model, and probably as good as anyone, unless you have a very good reason to assume a different type of noise profile. So of course there's lots of extensions one could do. So I think that actually it's not new that people say that it might be interesting to look at these epsilon expansions of orbits of dynamical systems. Although I've been talking to some people that have told me, yeah, people have looked at it for a long time, and there was little that they could do. So it's not. Of course, it's a very natural idea to look at such things, and of course, there's topological methods. All kind of ideas of epsilon balls and chain recurrence and all these kind of things. The question like, what can you really do with it in terms of these kind of problems? Apparently, some people think it's limited. I don't think so. I think that actually we can do quite a few things, and I will try to show you some of this. Anyway, so this is just an elementary example, just to make sure to kind of get some feeling that these things exist. So if I have just a uniform contraction, I add some noise. I just have, for example, I have a uniform contraction in the plane where everything is greatly contracted, and if I then had a ball attraction, then I get some invariant sphere, and this is unique. That's not what's obvious. It's an obvious application of this result. Okay, so the question is that if f depends on external parameters, how do minimal invariant sets depend on external parameters? In particular, can you say something about generic behavior? Are there bifurcations, and if so, how can it be characterized? Okay, so let's look at this example. So here's this curve. This is just x and y. This is the curve f of x, which is this function here. And I'm making again plots that I made before. So if I just vary here, I see this kind of pitchfork bifurcation going up. I see now 3 fixed points, and before I had just 1. And so this is the pitchfork bifurcation for this mapping. If alpha changes value, and sigma is 0. But if sigma goes up, I get this kind of upper curve and lower curve. I have the range in between, and so now my points map into these kind of intervals, and this has precisely with sigma. And I have minimal invariant sets. I can construct them here relatively easily by precisely finding the stopping points at the bottom and at the top, and between here I can just move freely. And as we saw in the circle example before, we have this behavior that if I now change the parameter, that my sets can change continuously. But at some point, what can happen is that I can just jump over, and you see here we're very close to tangency of this curve, and also this curve, at which point this whole thing just breaks up. And so what you see in this example is that we have a well-defined bifurcation of the set in some sense, and we should maybe define what we mean by that, but it seems to be clear that we have some kind of continuous behavior of this interval growing until it stops at a certain point, and then suddenly it explodes. And so what it means for this equation is I have a stationary measure here, a stationary measure here. They're independent, so points get attracted either here or there, and then what happens is after this point we still have 2, and then suddenly we have 1, and then suddenly we have only 1 stationary invariant measure. So all points get attracted to something here. Now of course, also underneath on the random dynamical system, also something happening. Because clearly at first I had 2 objects that will be in this case be random fixed points, because the one-dimensional case not much else can happen. But then when they merge, they can merge also into 1 random attracting fixed point on this measure. There's not much else that could happen. But of course in higher dimensions, so much more complicated things could happen. So here's a definition of topological bifurcation of of minimal invariant set. So it looks a little bit busy with words, but let's go through it and see what we mean. So I think this is a reasonable definition. So what do I mean by bifurcation? I mean that if my sets are not my invariant sets are not similar to what before. Let's say two systems are similar if basically they're kind of like related in a nice way. So how do they related? How they're related by homeomorphisms. Homeomorphisms are invertible maps. They kind of make one situation to the next thing, and they kind of leave things the same shape. So let f lambda be a continuously parameterized family of set-like mappings. And let script and lambda denote the union of minimal invariant sets. And so these are the things that I'm looking for all the time. We say that f lambda admits a topological bifurcation of minimal invariant sets at some parameter value if for any neighborhood V of the lambda star there does not exist a family of homeomorphisms H lambda. So this is invertible maps. Depending continuously on lambda with the property that these invariant sets we have at this lambda star are just homeomorphically mapped to those of values nearby. And so when my invariant sets are similar, there's easily a homeomorphism that maps my invariant sets to each other, but when suddenly they glue into one, I cannot map with a homeomorphism two invariant sets into one invariant set. Because it will be invertible. So this doesn't work. So we have just an example of this, but this is I think the most reasonable definition of topological bifurcation. Are two pictures the same? Well, they're the same if there's an invertible transformator maps them into each other, plus some continuity restrictions, which are also quite natural. You don't want suddenly that these transformations are not continuous in lambda, for instance. And you want the transformations, because if the set suddenly jumps, you think that's really a strange thing. So you want transformations, the homeomorphisms to be continuous in lambda. Okay, now the question is that we set up a notion of bifurcation which is natural. So can we do something with this? Because it's nice enough to introduce a concept, but then maybe we cannot really prove anything. But at least we saw that we have an example. Right. So. But I'd like to kind of, before I first look at this example again and make a comment, and because there's something missing. So in the visual bifurcation, we have two stable points branching off from a stable point, and an unstable orbit also exists in the middle. And I've been very quiet about this unstable point. So the question is, what happened to this unstable point here? And so this unstable point, unfortunately, doesn't give rise to an invariant set. So here's my unstable point for my deterministic system. But if I look around here, and basically all points either go here or they go there, depending on which realization you choose. So only if I choose the one map, of course, that sticks here, then I would kind of stay in here. But actually, it's not an invariant set. So if you look at the set value map, it doesn't really go there. Points go here, points go there. So of course, if I start with an initial set here, it becomes a larger set, which is also invariant. But there's some set here that I take will spread out. It will be an invariant set. It has these bounds, but of course it will not be minimal invariant. And so again, there's a slight difference also here between attractors, for instance, of the set valued systems and the minimal invariant sets. So the larger set here, for instance, is an attractor. But these smaller sets are minimal invariant sets in the stationary matrices of those things. So there's a bit of a problem somehow. So then maybe we think like, okay, we come from the deterministic case, you have this kind of attractors and repellers. Where's my repeller? There's no F invariant set here. So I'm somewhat lost. But it turns out that there's something else, which is not, there's not an F invariant set, but there's a so-called F star invariant set. Let me define what this is. And this F star for the set value system somehow takes on the role of the inverse. But it's not the inverse. But we'll see that it is related to the inverse in a reasonable way. So take some set value mapping, and then they call the dual of f star, and it's such that f star of x are all points y, such that x is in the image of y under f.
So this capital F is in previous slides from k over e to k over e.
Yeah, sure. Okay, but I let it be generated by 1 point. Of course, sorry. It is also a map.
So sometimes you distinguish.
Yeah. So I'm interested in set value maps. But it's also generated in some sense by a point, right? So I always define the thing on the set as the f of u is the union of x in u f of x. I always have a description in this form.
So when you talk about the dual of a set value dynamical system, you need to go back to the generator of the set value dynamical system.
Right. Well, I can of course, you can of course write it out what it means for a set. Figure out for a set is just the union over x over all these things. Right, and then I can write these things also out. It's not a problem. If I write it down for 1 point, and I adopt this notion that m sets is basically just taking unions, and then it naturally follows. So it's just a consistency. Of course, I insist on this relation. I insist on this relation that for a set, it's the same as union for points. It's not ab initio clear that this should be any set value mapping may not have this property, but I want this. I want to make sure that we have good behavior. So then it's enough to just define it for points. But of course, it is because after one iteration, I handle with a set and I just add external sets. But always in this sense. So maybe good to notice that if it's just 1 point, if we just don't have the epsilon ball, the sigma ball, then of course f star is precisely f inverse. But f star is not the set value inverse of f. So f star composed with f is not the identity. And also importantly, in f star, in a set that's invariant under f star is typically not invariant over f. Okay. So why did I introduce this? Because there is a so-called f star invariant set. And the f star invariant set sits over here. So how do I find this f star invariant set? So the relation is basically just the other way around, right? So this relation of f star switches the things around. And so what do you do in the graph restriction? What I do is I flip the graph. I flip x and y, image and the domain. I just switch them around, and then I find an invariant set for the switched around system. So if I look sideways, I just go from minimal to optimal curve. But of course, then I'm interested in the range of this. So the f star invariant set is very similar to this set, but that's for the flipped around system. Okay, but now we see suddenly what happens. If they have this bifurcation, we see these invariant sets here, and we have now this kind of f star invariant set sitting here. And when we have a bifurcation point, when the tangency comes up here, then we see that these sets precisely touch, and when they touch, they just disappear. Right. So what we see, if you have this kind of picture, is something just for the example. I have here f invariant set bifurcating. It bifurcates under the collision with this f star invariant set coming from the other side. So it just doesn't come out of nowhere. And this is very reminiscent of kind of like Moore's decomposition type theories. And yeah, so you can build on this kind of notions, some kind of Moore's theory for set-value systems. Okay. So what's the dynamical interpretation of this f star? So I know that for the dynamical system on sets, it's not the inverse. But the nice thing is that it is actually the inverse. It is a set valued mapping associated to the inverse of the random dynamical system. So this is what this lemma says. So suppose you have a set valued map generated by a random dynamical system, and I here take this, just for convenience, the iterated function system that we dealt with, for instance, on the circle. So we just have a certain parameterized family of maps, and let them be invertible. Then this is the definition of f of u of a set. So this is the image of the union over x over u and alpha and delta of this thing, and then the f star of u is thus this union over the inverse of these maps. So this is kind of nice. So we see that actually, so this repeller is actually some kind of the minimally variant set for the time reversed random process. But it's important that this thing. But if you compose these things together, then it doesn't lead to something trivial. You don't really. It's not the inverse for the dynamics. If I have some diffusion in one way, and I take the inverse process with the diffusion as well, it doesn't lead to everything shrinking back to one point. It leads still to some diffusion. So there's a dynamical interpretation of that, which makes it quite natural to use that. And so the proof is very easy. So this definition of f of x, this definition of f star of x, and I just write things out. F star of x is the y, such that x is in f of y, then I write f of y union of alpha of y. This precisely means that y is f alpha inverse of x to some alpha delta. Right, so this f star there, the f star map is precisely associated with the inverse process. So I just wanted to kind of show you another example which I didn't put on the slide, but that I can draw by hand with some confidence. Just have a mapping so you have x and one is a plus n squared plus some noise where psi and sigma. Then you have a centralized system like here. And so what we have here, we have a f-invariant set. Sitting over here, associated to the tracking point, and we have a f star invariant set sitting over here. Just basically also the point was just in the opposite order, because if you look to the flipped system, you look from the side, you have the lower curve and then the higher curve. And here's the, so you have an f invariant set here. And if I then go to the state where we have the bifurcation point, so if now this push this point up to here.
Is this left one f invariant?
Sorry?
The left interval, is it f invariant?
And this is the lower one, and this is the higher one, yeah.
Yeah, but the higher one, the image of higher one.
But this is not f invariant. This one.
No,
is
the left one.
Yeah, this one, yeah.
Yeah, but right end point of the interval, the image of the right point of the interval strictly bigger than the interval itself, right? Because
here, I draw it wrongly. Probably.
let me call the interval AB.
Yeah, sure. I see what I think I'm drawing it properly. So the other way is.
So I think you strictly make the interval larger.
Yeah, this the it's wrongly drawn. It's wrongly drawn. Sorry about that. It's wrongly drawn. But it looks like this if you draw the graph properly. Sorry about that. Yeah. I'm sure we can do it. I will draw it properly, and then I will. It is. You have the tracking peak point here. The smaller than you have like around here. The tracking set. You have here expansion. You have the invariant set sitting here. If you draw the graph properly, if I draw it not properly, it will not have a. It will have other behaviors around it somehow. I have to have the situation that I do usually have a unique fixed point. Because I draw my parabol a little bit unpleasantly. Shouldn't be correct. I'm sorry about that. If you draw it properly, I'm sure it's correct. So we have the situation where we have a unique fixed point for the deterministic system in the middle, which is contractive, and here it's repulsive. Then around this point, in this construction, we'll have an invariant set, F invariant set, and this point, around this point, I have an epsilon invariant set. Modulo my artistic interpretation, which gives you the wrong picture. I'm sorry about that, but I'm sure we can. I should maybe have drawn it properly with MATLAB or something. Anyway, what happens then if a tangency appears, but you will see it precisely that the tangency will bring these 2 points close to each other. Right? They bring them close to each other, so you see that this F star and the F invariant set will meet at some point, which is similar to this other example. So these are two very simple examples, but they're very important examples. We'll see in a theory. So my claim is actually in some sense that we can make some kind of theory of these bifurcations, and these two examples are very typical for whole classes of examples that behave similarly. Okay, so the questions that are called urgent questions. So what surprises me to some extent when I start working on this, that you think this is so basic that everyone must know a lot about things about it, but it seems to be not something that people really have worked on so much. This is a surprise. It's also a good lesson, I think, for everyone who is below a certain age, that never be shy to try to do something that you think should have been done by someone else years ago. Of course, because it's so obvious to do, and this just happened that, of course, some obvious things have been done, and some obvious things just haven't been done by anyone, because science is a business of people. That's not logical. So, okay, so can we classify these things? And another important question is, like, how can these bifurcations be characterized? Maybe from the invariant set. Can we say something about boundary properties? Okay, here it's not so interesting, it's just intervals, but in higher dimensions we can have more complicated shapes. Is there something of the shape of the invariant set tells us something about whether we are close to bifurcation? Or can we say something about just those dynamics that sits inside an invariant set? And can we pick up properties of the dynamics inside an invariant set that tells us that we are maybe close to an instability of the set-solid system? Another very important point is, can such minimal invariant sets be computed and tracked efficiently? And this is a surprising problem. It's not so easy to compute such objects in set-valued systems. It's kind of expensive. So there's all kind of things that can be done, of course, but most of them are not so inexpensive. The question, like, can you do something? For instance, you have an invariant set, and I change the parameters. I suppose there's no bifurcation. I would say, like, can I continue the shape of this invariant set as a function of the parameter? This is kind of expensive computation if you do brute force. So the question, like, can you do it in a smart way? So then you need to know something more about invariant sets to understand how to continue. Okay. Of course.
You have two ones.
Two ones. Oh, yeah.
One.
They're both very important. Yes. They're both very important. Equally important. Okay. So I want to say something about. So in one dimension, my invariant sets are just intervals, right? And they must contain at least an absolute ball. If I have such a some ball, if I have this expanding map like a d sigma on it. So we just have the kind of intervals. But the question, like, if you go to higher dimensions, how do things look? So in high dimensions, things are very much unknown, but something is known in two-dimensional case. And so here's a result. So if I have this kind of two-dimensional setting where we have the same kind of random system, and we do the set valued mapping for it, then we observe the following. First of all, the boundary of an invariant set is a Jordan curve. That maybe not so surprising. So it's a homomorphic image of a circle, of a compact set. So it's like, for instance, it's not like a fractal or something. It's not like a Koch curve or something. But it's a reasonable boundary. And the second thing is interesting. The boundary is piecewise smooth, and the points of the non-smoothness are wedge points. And this is quite surprising. That is actually that is something that can be said like this. And I'll show you a picture. So here's precisely what happens at a wedge point. So we have kind of points of, here's the boundary of the invariant set, and here's a boundary continues. And we can have such points which are wedges, which are not differentiable here. And how does this happen? Well, it happens because if I look at an invariant set, what happens? I have two maps. First I have a map F, and then I have this kind of expansion map with poles. So the dynamics is like, what does an invariant set look like if it's first doing F, which has to be some kind of contraction within, and then expand the set, and then it has to sit on itself exactly. It's like, what does fixed point look like? So typically on a boundary point of such an invariant set, either you have a one-to-one relationship between the point on the boundary and another point on the boundary of the map on the little f. Little f is just the, say, deterministic map. And then if I expand it with balls, I get a unique relationship between one point giving rise to another boundary point. There's a one-to-one relationship between the image of the f image and the ball. But if this relationship is not unique, first.
Do you assume the deterministic map f, little f to be smooth?
No.
Why then the boundary minimum set can be piecewise smooth?
It's piecewise. Sorry, it's yeah. That comes from the balls. It's a bit like diffusion. If you have diffusion, I can start with a very rough initial condition, and if I flow it forward, it becomes smoother to the equation. So if I have a rough curve and I make an epsilon ball cover of it, it's got smoothness the boundary. It's the same as diffusion. So sometimes it's true that if you have something which is rough, and let's sort of operator act on it, it becomes better. Okay, but it's not everywhere differentiable. It's not differentiable on such points. And these points are not differentiable because I have two points that contribute to this boundary point. And I have 2 points that contribute that have 2 balls that give you different tangent vectors at this point. So these balls will give you tangent vectors. And continuity of this curve gives you basically the differentiability here because you have continuity of the tangent vector.
So if the f is, if little f is just continuous, then the f of m, the boundary of f of m can be much more wild.
Yeah, it can be more wild. But then,
still, you say that the boundary of M.
yeah, because the tension factor on the point that associated with this depends continuously on the underlying curve. So the balls give rise to a certain shape of the boundary, and they give you basically a tension factor. So if I change here a little
the
bit,
creation of the tangent vector is okay, but there may be lots of tangent points like this which may accumulate.
yeah, that's possible. Yeah.
Then the boundary of M cannot be. So what depends on what you mean by piecewise smooth.
Yes, it's outside the wedge point. Is of course, it can happen in
Okay, so you don't say that the singularities are finite when.
No.
Oh, then okay, that's
no. I can have accumulation point. Of course, I can construct an example where I have an accumulation point of wedge points. If I make a very rough boundary, I can make something accumulate to this point. Yeah, but between. Sure. Yeah, so that's what I thought. But it is nice. So what I think is nice is that you have a certain visualization. So in general, this problem is hard. If you have a set value map and you look at the invariant set, you can say nothing, really. But if you say that they're balls, suddenly you can say something. So you have a little more structure. And it's my hope that with a little bit more structure, you can say, well, why would you care? But I think a little bit more structure. Maybe this can help us to compute, for instance, set sets better. Because the more we know, the better we know where to look. And we can maybe then, so this is, but now for instance, in the higher dimension analog, I don't really have any answer. So I don't know precisely. Of course, we can extend such things into higher dimensions. We can also see such wedge singularities with the co-dimension one series, but we don't really have yet a systematic classification of singularities that happen in higher dimensions. So the state of the art is really limited still. Okay, just want to give you another example of a picture to kind of emphasize that you see something here. This is a random Henon map. It says a period 2 point, and this is, for instance, a very expensive computation, unfortunately, but the brute force to just calculate a minimal invariant set for this Henon map. And if you change the parameter, then it's like to convince you that something happens which is reminiscent of what we just saw one dimension. It just changes basically smoothly if you change the parameter, and suddenly it explodes. And so there's an explosion of the minimal invariant set in a similar way as we saw in the other example. Okay. So what I'm going to do in the second hour is actually give some more mathematical detail about the analysis, that some theorems that come from this paper. Which actually gives some more detail about these things, and maybe a starting point for some kind of like bifurcation theory for such other systems. Okay, so I think it's time for a break, and then I'll go.
That's maybe 10 minutes after I have.
Yeah, sure. Some results that underlie some of the pictures that we saw in the example. I would say it's not a full-fledged complete description, but at least it gives a good sense of the behaviors we see. So let me kind of first set up the settings. So we have a assumptions that it's continuous.
t cross x to x or t, k of x?
It is k of x. And we have the usual. But of course, it's defined on sets. So. Usual set, right? So for point, it's just a union. It's just a point.
So for H2, you set the image of single point to be just a single point itself as a set.
It is just the identity map.
You don't make any inflation.
If time is zero.
Time is
If time is zero. So after time is zero, nothing happens. So this also allows for some kind of differential inclusions and stuff like that. That's not necessarily discrete time. Okay, so time could be maybe just positive. Okay, then a note. So 5 star, designed as before, satisfies H2 and H3, but not always H1. But H1 is satisfied if in this, for instance, if the constituting think of the case where you have a iterative function system. If these maps are not invertible, then I don't have necessarily continuity of the F star map. So if my graph of the map is like this, then we have continuity this way, but if I turn it around, I get a point of discontinuity just because of non-invertibility. Okay. So we have no invariance. We call the invariance like minimal. If that doesn't contain a proper invariant subset. And we'll, under reasonable conditions, go for the distance, right? Okay, so now I want to say something about the tractor repeller decompositions. So the objective is to define the domain of attraction for set by the dynamical system so that complements our repellers. And the repellers are defined to be phi star invariant things. So they're not necessarily phi invariant. So the objective is to define invariant set such that complement is phi-star invariant. So the domain of attraction I will call A M, and where the invariant set is called M, and complement is called M star. This is X minus A. Okay, so the definition of A-ban will be, we'll do as a given definition of A-ban and then show that this basically works. Definition. V-ban is all points such that all P were observed, the system includes of px such that the limit into infinity distance equals 0. So importantly, it's not just that I ask for things that attract, but they have to kind of stably attract in some sense. And so it's not true that just I look for all points x that attract, that compose are to V, but I want that around the whole orbit of x, there's a small neighborhood that also attracts to M.
This capital P is a little p.
Sorry, but yeah, sorry. There's only one P here.
Yeah.
Sometimes I get ahead and sometimes not.
Limit t goes to infinity, but the
Limit for sort of P. So then I have M star.
actually, so in the definition of A of M, so the small v is any element of the capital V, is it right?
Sorry?
So the limit of distance between phi of t, so that's a v, small v.
It's a V.
V is an element of capital V, is it right?
So the set itself.
Set itself. Okay.
Yeah, what's the role of this capital T? You say for any t bigger than or equal to 0, there is a neighborhood of V, which is a neighborhood of phi of capital Tx. Why not just take a neighborhood V is a neighborhood of little x, and then ask this distance go to 0 condition. Do you need the capital T?
Well, I just parameterize, so along the orbit I parameterize here with capital T. I give a neighborhood for each such thing. And then here, okay, just take a limit over small.
Okay, so you flow it forward for any some fixed time, and then take a neighborhood, then you require that all these.
The neighborhood is around each point, right? There's a neighborhood around each point.
Yeah, so the capital V depends on capital T.
Yes. I take an orbit, and I want to find the neighborhood of this orbit, so that this neighborhood also turns. Proof. Conclusion. So you have to show that this is true. Contradiction. To assume that there is a point which sits in this set but not in M star. This of course is the first observation is that IP of X this time is not empty, but at the same time we also have fixed factor, but this contradicts the path that is invariant. Right, so that gives you one part of the inclusion. Second part. Assume that this t greater equal to 0, so that now x m star nothing. This guy. Oh, then we have the section with m star empty. And this follows that f star dx a and star. Now we show that. This implies that this will be an and this is a contradiction. Since x was supposed to be in m star, which is x times a. Okay, so we have to divide it up into two pieces. So basically, it's going to go look at the construction of these, follow these kind of neighborhoods, and see whether or not we can make this work. So t, sorry, at t positive from 0, and first we consider t small equal to still t. Since A was open, and the map IPX was inside, compact, then there exists some gamma such that the gamma neighborhood define Tx is also an. Now these two properties, first that is phi is continuous. Secondly, just the composition property. Because I'm going to just basically map neighborhoods around. So this is on the neighborhood on stop. A minute. This is my x. Then the delta such that t minus 3 to the neighborhood. So this is basically a whole set of neighborhoods which are now attracted. So they have neighborhoods of the orbit is now can all be attracted. This implies that the X is indeed in line with the contradiction that we were looking for. So we So we just need to check that other case. Easier. Because here we have to backtrack. In the first case, we have to backtrack. Now we just kind of move forward. So since X in the case of the fraction, hence the base of the fraction is fine variable. We have dx equals compact. It's what's in the name? It's a subset of AM can exist compact neighborhoods of is attracted by so here we get this one, and the other. Okay, so this basically gives us then a way to kind of divide the space into basin of attraction of sets and the complements got the appropriate invariance properties. So the problem is that if you don't take this neighborhood somehow, you can't get it to proper. So you need this stable setup here. Good. Maybe I switch this around. So in principle, the idea is that one can build some kind of more decomposition theory just based on such things. But I will not dwell on that further, but at least we have the kind of derived objects now. What I want to do further is talk about the dependence of the minimal variance set on parameters. Okay, so that can be complicated if you don't put any structure on a set-size map. If you just have set-size maps, it's quite a wild business. And you have to put some additional hypotheses which are reasonable for the types of applications that we're interested in. So first, let me say we consider some family. Of satisfied systems, and where I take some kind of space here, and then I have some additional hypothesis. There's H4, that's it, that's continuity. Forming final condition that we need is that we make sure that we have not a single value system, and we have some minimum volume in the set. So I'm going to require this guy contains all positive ranges. All dx. And positive 9. Moreover, T absolute such that phi lambda Tx contains it all. That's absolute. X. And so this the simplest case precisely to have discrete time and a map always to sigma balls and sigma z. Okay, so now I find m lambda as the union of all phi lambda invariant sets in this. Then I have a theorem given family phi lambda.
Is it union or collection?
Sorry?
So discrete M is
Collection,
a
sorry.
collection.
It's the union. It's the union of all phi lambda set. It's a set that contains all invariant sets. Given this family, satisfying H1 or H5, and that m lambda infinity in element Oh, no. Not fine. Sorry. Invariant sets are not, of course, many invariant sets. It's a union, union. Sorry. Because I have invariant sets which are subsets of other invariant sets and so on and so on. So I just really like the collection, and then I've got to take a subset here which is minimal invariant set.
Lambda infinity.
So A is infinity. And for each sequence, n by n, converts into an infinity. There exists subsequence and k. And the delta positive such that one of the following holds. One is that we have lowest simultaneous dependence, the following sense, and that's going to be contained in these naming big infinity of the union invariant sets intersecting with the delta neighborhood of this object. Now, what I expect. Second possibility of instantaneous appearance. Won't be set at the end. Okay, so it's a whole mouthful. So basically what it says is that we have some scheme where I vary parameters, and the question is like if I approach to a certain given parameter L infinity, if I approach other parameters, what happens to my minimal invariant set? And the two possibilities, either we are lower semi-continuous in this sense, and this contains the case that we just have basically are continuous. So it contains the fact that basically this set evolves continuously. but it doesn't need to be, but it could be. And this one is a very abrupt change. Okay, so the proof is in my paper with Rasmussen and Rodriguez. I will not give this proof because it's a bit tedious. But I will give you some examples to show that this actually happens and related to the examples we just saw. So at 1, we will look at pitch application. So we have some kind of involvement like that. Let me draw that carefully. So that is another thing to be here. Then at this point I have an invariant set which is precisely this and this. Not quite a bit. It's just in the middle, but afterwards it's like this, and then if you approach it from this side, then we have this thing that the lambda infinity is contained in the limit of this thing. So I extract this thing, and at this point itself, I just miss out this lower sum continuous. Of course, if I come from this side, then just continuous, right? If from this side, it continues, because it's just these 2 points. And then if I jump, then I jump into something different. But if the limit here is continuous, and here lower sum continuous. So, and this also we saw in the Henon example, basically. Yeah? The same kind of picture. I'll do the saddle node. What did we have there? We there have basically one invariant set that just basically collapses. And here I take lambda and for backwards. So on this side, you just have continuity, no problem. From this side, I have sudden appearance. I come here, at this point I have nothing. That's why we have the empty set for all approximates. Even on the limit, I have a whole set here. And so this is the instantaneous appearance of an invariant set. Okay, we looked at it from the different point of view. We said, well, if we don't have an invariant, we have an invariant set that just disappears. But from this side, we just have continuity. Because whenever we try to define a point, we find some tree set which is similar. But if I come from this side, it's not. There's nothing, and suddenly there is something. And it's you can't keep coming. So to prove this kind of thing, it's used similar. I did this the first proof in detail. Why? Because you can see a little bit what kind of arguments one uses, and these are the other proofs. They're in similar style. So there's nothing spectacularly technical about this, other than it's tedious to keep track of all the facts. Okay, let me That's on board. So question. Right, so let me just re-emphasize. So in case 1, case 2 we always have something like bifurcation, because you see that they have a drastic appearance of a new set. Always leads to kind of complications with, and my definition of bifurcation was that I have a continuous family of homeomorphisms. If some invariant set suddenly appears, of course, I will be breaking the condition of no bifurcation, so I'll have a topological bifurcation. Under the conditions 1, I have 2 options. Either I have a bifurcation like here, or I just have no bifurcation. So every limit point particularly in the middle also satisfies condition 1, which just says that they have continuous dependence. So if I look at the cases with non-discontinuous dependence in the Hausdorff sense, then I can look at this condition excluding the equal sign. Then I have some kind of discontinuous bifurcation in Hausdorff sense, and the second case. So I could isolate those.
So you assume lambda infinity is not empty. Empty set can be called a minimal invariant set. In the theorem, of course, you assume that is non-empty.
Let's can the well, if the empty set would still, I don't know if I'm good, but it would still be okay.
The important point is that is not empty. Empty, and then the limit is empty. Limit loop is empty, but at the lambda infinity there is no empty minimal invariant set. That's what you want to say.
Yeah. Here you have empty sets, and then you convert it to a non-empty set. Yeah, but I think there's not a problem if you include empty sets. Is there a problem?
No, not quite, but at least
it's not what you want. Yeah. Okay. So we'd like to still know a little bit more. I also want to say something about the F star invariant set. Maybe the first question is, can there be continuous merging of two mini invariant sets? And the answer is no. Maybe the proposition is if you suppose we have the all conditions satisfied, then we have two invariants, two minimal invariant sets. Composed of lambda, and for all lambda star, we have that the limit of lambda equal to lambda star of the interval of xy in N1 2, the distance between points is always greater than 0. So if you have two minimal invariant sets, if I vary the parameter and they're continuous, they cannot collide. They cannot. There's no lambda star for which is the distance, the minimal distance between two sets, close to 0. It's always bounded by something, so we prove that we not. We just cut it a bit short. So the problem is that we have these, if they approach each other, they approach each other at a point x. Point x, then for lambda sufficiently close lambda star phi t star a single cycle over and 1 lambda and m2 lambda. Because it contains an open ball of equal size. And that is a contradiction of invariant of M2. So we have a problem that we have a point where we converge to, whereas there's a point that actually will blow up. And this, for the blow up, they will map both in these two sets. But it also say that these two sets are minimal invariant sets, and that leads to a contradiction.
So you use H5? That's what you mean?
Exactly, yeah. H5 is crucial to have this kind of satellite approach. Of course, I could have just a usual map, just a one-to-one map, and then all these things are definitely not true. So it comes because we have some flattening, and yeah, so it's essential that we put that in, otherwise we don't have the result. Okay, so the general world of satellite maps, of course, is rather complicated, and as is the world of random dynamical systems. And I think it's highly advisable that we seek results in context that actually help us to understand something rather than just make it more complicated. So general random systems are extremely complicated if you don't have any control of the type of noise we allow. As are satellite dynamical systems, if you just say, well, any set, and that makes it much worse than we had before. And I'll have to think about wrapping up. I will. So this is the thing. So that there's another other thing we saw. So for instance, these two sets, they come together. You see, they can't really come closer than something because there's actually something in between that stops us from getting there. And the final result that I should mention, because it is important, and I have discussed it before. Because this contains modifications in the Hausdorff method, meaning we have case 2 of the previous theorem, or case 1 with a non-equal in inclusion, then and lambda infinity as a so if we have a bifurcation of the minimum invariant set, which is continuous in